I think there is another explanation that we can draw from science. Okay, so why do we have a single universe precisely designed for life? We need to re-examine how the universe began. Did it require an intelligent design or not? What does Judaism say, and what does science say? Judaism tells us that the universe was created by God, an infinite source. In fact, one name of God, the Yud and the He and the Vav and the He, means all that is, was, and will be. It is the definition of infinity. Look in your Art Scroll Siddur on page 178. This is so important to Judaism, it is listed on the 13 principles of faith. The second and fourth principles imply that God is infinite, beyond space and time. Something every Jew must believe and is part of the definition of being Jewish. Pretty important. In order to have a real and permanent universe, according to Judaism, God's infinity must be involved. And recall what we learned from class 1. Judaism also tells us that God introduced a one-time event that was critical in the formation of the universe, and that it will never occur again. And science? Can science give us any explanation for the existence of our universe? We need to spend some time reviewing what science has to say about this. Firstly, we need to review and understand something important about science. Science has shown us that when we try to understand the nature of our universe at its roots, we find that intuition is not very useful to us. Recall what we learned about relativity. We found that we developed within an environment that did not involve speeds approaching that of light, and therefore we have no intuition with it. We also evolved in an environment that was not on the microscopic scale of an atom, which is the size the universe was when it started. What happens on that scale may also not be one that we can guess at with our intuition either. Stephen Hawking recognized this, and was quoted as saying, and I will paraphrase here, "Do not be fooled by what you see. What you see is not reality." Interestingly, I have found that Judaism holds the same view. The same quote can be attributed to my rabbi. "Do not be fooled by what you see. What you see is not reality." If you think the religious narrative on creation sounds crazy, science sounds crazy too. When it comes to events on the atomic scale, science is going to ask us to believe things that we consider to be impossible. Like Alice in Wonderland said, a healthy attitude is to try and accept one impossible thing every day. In other words, as I explain this, please try to keep an open mind. In order to understand how science sees creation, we must understand the underpinning ideas from science. It isn't that hard. You'll be surprised to learn that it's based on maybe 5 experiments and a few simple rules that may sound crazy, but happen to be reality. Remember that because the universe was smaller yesterday than it is today, at some point everything was packed into a space smaller than the size of an atom. On that scale, we need to know what things that small are like and how they behave. This is the world of quantum mechanics. Quantum mechanics describes how atomic and subatomic particles behave. So we will go through the rules of quantum mechanics. The rules are very weird and do not agree with our perception of reality, but they are as real as we are. The first rule is that everything is both a wave and a particle at the same time. To us, a wave is a wave, like a water wave, and a particle, or a solid object, is a solid object. In reality, everything is a little bit of both. Sounds strange, but true. This was first discovered looking at the nature of light. Waves and particles are how we get messages or signals from one place to another. For example, if you're on a river shore and want to tell a man sleeping in a boat on the river that a storm is coming, how can you do it? You can make waves in the water that will rock his boat and wake him. That would be a method of sending waves. You could throw a stone at his boat, shaking the boat and waking him. That would be a particle. In fact, any way you can think of to get a message to him is by wave or particle. On the human-sized scale, waves and particles are different. And we know that we can send signals fastest with light. So what is light? A wave or a particle? Scientists needed to know. So here is our first experiment. Take some marbles and fire them at a screen that has 2 slits in it. The slits are just a little bigger than the marbles. There is a screen on the far side where the marbles can make a mark when they hit. If you do that, you will notice that where the marbles go through the slits, there is a corresponding band of marks on the far screen. That's common sense. It's common sense because we live in a world with life-size particles that do this. This is how waves deal with 2 slits. If instead you create water waves from a point source that approach a barrier with 2 slits, each slit will act as a new source of the wave that struck it. Waves have the ability to interfere with each other. If a high point or crest meets another high point or crest, it forms a supercrest. This would leave a big mark on the screen. If a low point or trough meets the crest as they strike the back screen, they cancel each other out, and the water is still. No mark. It will form a series of bands on the far screen, bright areas where the waves were reinforced and dark areas where they cancelled each other out. Which do you think light does? Is light a particle or a wave? Light, as it turns out in this sort of experiment, produces all those bands. It must be waves. One problem though. Einstein showed that light can be used to strike a metal plate and create an electric current. He proved that there were distinct units, or particles, that would strike the metal plate in something called the photoelectric effect. This is a real property of light. Light is made of particles called photons. Alright, so which is it? A wave or a particle? In fact, it's both. This is not intuitive to us because we don't deal with particles that small in real life. In fact, any particle of matter, like an electron or proton, can be shown to have a particle nature and a wave nature. It can act like a wave or a particle depending on how we set up the experiment. You can take electrons and make them pass through 2 slits just like light did, and produce a band pattern on the far side that makes it appear as though it's a wave. So what in fact is waving in a particle? This is a hard part to explain. I'll try. It's called the probability of existence. Matter has a wavy nature because of something in quantum mechanics called the Heisenberg uncertainty principle. This states that we cannot know exactly where a particle is and exactly how fast it's going at the same time. The more accurate we are with one, the less sure we can be about the other. This is not because we're not measuring accurately. It's because if we try to measure one quantity more accurately, the other literally gets blurred out. So here's how. Say we have a particle that is really small, like the dot on the left side of this picture. Now let's magnify it so that it looks really big, like the oval on the right. That particle can also be described as a wave of energy, and so I've drawn inside the particle its energy wave. The wave of energy has a size 2, and that's its wavelength. The energy tells us how fast the particle is moving. The oval tells us where we will find the particle if we look for it. For really small particles, like atoms or protons or electrons, the size of the particle and its associated energy wavelength are close to the same size, and that's why we have this problem of not being able to know where something is and how fast it's going all at once when things are really small. For example, in this magnified view on the right, we could say that we want to know exactly how fast the particle is moving. To do that, we need to be able to measure its entire wavelength and see the whole wave at once. At this magnification, though, if we look at the whole wave and then ask, exactly where is that particle? It could be anywhere where we see the wave. In other words, inside the whole oval. However, exactly where inside the oval, we can't say for sure. Now let's narrow our search for the particle. Let's say we look for it only on the left half of the oval, and we find it somewhere in there. Now we're a little more precise in location, the left half of the oval, but we are only looking at the left half of the particle and wave. We now can only see half the wave, so we are not as sure as we used to be about the energy and therefore its speed. The more we narrow our search for and limit the location, the less wave we can see and the less certain we are of its speed. We can never know both position and speed at once. The bigger something is, the shorter its wavelength. So the uncertainty in the uncertainty principle is very small for big objects. Big objects have really short wavelengths. That makes the uncertainty in the wave unnoticeable, because compared to the size of the object, the wave is very small. For example, if you are accurate in the velocity of a bowling ball to 1/100th of a meter per second, the uncertainty in its position would be 0.0000000001 meters. The uncertainty is so small it can be ignored for all practical purposes. Large particles behave like the particles we live with in everyday life.